Thank you, Zachary, for the introduction. So I'm working for Buildwise, formerly known as the Belgium Building Research Institute. And I will talk to you about how to improve the supplied ventilation air through filtration. Here's the outline of my talk, and I will start with talking about why should we care about air filtration. Caring about air filtration all has to do with caring about indoor air quality. And there are three major cornerstones to obtain a good indoor air quality. The first one is to minimize indoor sources as a most effective measure, but of course we cannot prevent the formation or release of all indoor air pollutants. Therefore, ventilation plays a second important role in diluting and removing these pollutants. Now, within the basic principle of a ventilation system, the polluted indoor air is removed, is diluted with outdoor air, and this outdoor air is always considered as a source of clean and fresh air. We know that it is not always the case, and although outdoor air quality improved in the last decades, some pollutants remain problematic, for example, PM2.5. As such, 96% of our European citizens are living in a region where the PM2.5 concentrations are above the guidelines of the World Health Organization. And this has a huge impact on our health. For Belgium, it's accounting for more than 8,000 deaths a year. So a third important cornerstone to obtain a good indoor air quality is to prevent the entry of outdoor air pollutants. And this can be done by filtration. In a previous study, we have shown that pollutants do enter via the ventilation system into the indoor air, but we also showed that there are possibilities to at least reduce this entry by filtration. But before entering into these results, I would first like to talk to you about air filter classification. Nowadays, there are still two classification standards in use. The old replace standard, EN 779, alongside the new standard. And within the old standard, filters were classified based on their efficiency for particles of 0.4 micrometers into three major groups: coarse, medium, and fine. I think filters like G4, M5, F7 as classes do ring a bell for most of us. So in the end, with this classification, we had 9 classes, of which 5 were often used. Nowadays, filters are classified in 4 groups, being isocoarse, EPM10, EPM2.5, and EPM1, based on their efficiency for particles within a size range. And within these groups, they are further classified in steps of 5%, resulting in a total of 49 different filter classes. This makes filter choice, of course, far from easy. So therefore, we see nowadays still the old classification and the new classification that are taken up into the technical sheets of these filters, meaning that these filters are still tested according to the two standards. If this is not the case and there is only one classification shown on a technical sheet, it's theoretically not possible to translate it to the other classifications due to fundamental differences. That's the reason why I will, in this presentation, whenever possible, indicate both the old and the new classification for the tested filters. Filters can belong to the same class, but they are also available on the market in different types. So as well for coarse filters as for fine filters, they are available in the folded panel format as well as the bag format. And I mention this because we tested in the project also the two different types of filters that belong to the same class. Next, I come to the major findings of a research project we've done on filters for small residential ventilation systems. Within this project, we did a 3-step bottom-up approach where we started with measurements in laboratory on filters as components. So therefore, we constructed a test setup in our Brussels laboratory that is composed of 12 parallel test lines. And in each test line, we have one or a combination of 2 filters. This whole test setup is fed with Brussels outdoor air, meaning that we did our performance measurements on the filters with the particles as they are present in the outdoor air. And we also did follow-up experiments throughout a complete year, so we also have an idea about the evolution of the filter efficiency throughout of time. If you want more information about this setup, you can find it behind this QR code that leads to a video on YouTube. I tried to summarize our findings of this project in one slide, and I will start with the results of the coarse filters. If we look at the graph on the x-axis, you see different particle classes ranging from smaller particles to larger particles, and on the y-axis, you see the efficiency of this filter for these different particle classes over a follow-up period of 13 months. So what we see for this G4 core 60% filter, we see that it's mostly effective against larger particles, meaning that this kind of filters do not really improve the quality of the supplied air. One exception might be pollen, since plant pollen are in general larger than 10 micrometers, so they are well retained by the filter. So these filters are mainly present in system to protect the system against falling. Besides, we also tested fine filters, and if you look at the graph, you already see that these filters are more efficient than a general coarse filter. And we also found that an EPM 155% folded panel filter or an EPM 2.5 70%, both belonging to the old F7 class of filters, are capable of reducing the PM 2.5 concentration in the supply air below the guide value of the World Health Organization, given the outdoor concentration in a city environment as Brussels. For the folded panel filter, it's very important to protect it with a coarse pre-filter to prevent a rapid buildup of pressure drop over this filter. But both the combination of a fine filter and this coarse filter or an EPM 70% bag filter are capable of reducing the PM 2.5 concentration. So from these results, there is no need for even finer filters. Now, how does this solution look in practice? We have one solution that's a combination of a coarse filter and a fine filter. In this solution, we will place the coarse filter into the system in front of the heat exchanger to protect the system and its components, and also the fine filters that is sitting behind. And this fine filter will be installed in an additional filter box that is added behind the ventilation system. In the second option, we do not place filters into the system itself, but we add an additional filter box in front of the ventilation system. And in this filter box, we place an EPM 2.5 bag filter. And this filter will play two roles at the same time. It will protect the system against falling, and it will also improve the air quality. Moreover, if we look at the pressure drop, we see that also this solution has an advantage. It has overall, over the long duration of the follow-up, a lower pressure drop than the combination of a coarse and a folded panel filter. You see it over here with an average pressure drop over 13 months indicated here, and the other values are the minimum and the maximum values. So this is an interesting solution if you're looking at protecting and improving the air quality at the same time. Now, for mid-size systems or air handling units, most of them use the same filter classes and types as we tested here, only there are several of them that are placed in a frame. So we can ask ourselves the question, do I have an equal performance of these filters in the air handling unit, or are there special points of attention? Now, before running into these results, I will also mention that we tested an electrostatic precipitator as an alternative for fine filters. These systems are commercially available to be coupled with residential ventilation system, and within an electrostatic precipitator, we have two parts, an ionizer and a collector. Within the ionizer part, the particles get a positive charge, and on the collector part, they will be collected on the plates because the plates have an opposite charge. We also tested these kind of systems, And the results show us that they have a high consistent performance on all particles within the measurement range, so from the 10 nanometer to the 10 micrometer particles. And it's also combined with a very low pressure drop when we compare it to, for example, an F7 filter. So this is a very interesting alternative to fine filters. So last but not least, we did within the smart ventilation project translational research to see to what extent can the findings from our residential project and our recommendations be translated to mid-sized systems. And this we did by a series of in situ measurements on different configurations. In total, we had 3 different configurations. One configuration is an air handling unit equipped with a combination of a coarse and a fine filter in folded panel format. A second setup is a back filter, an F7 back filter alone. And a third configuration is a test of an F7 back filter, but at different airflows. And this because of the difference between the minimum and the maximum airflow in an air handling unit is much higher than in residential systems. So therefore, we wanted also to look at the influence of the airflow on the efficiency of the filter. So in the first setup, we equipped the system with an M5 coarse filter before the heat exchanger, and we placed an F7 folded panel filter after the heat exchanger. On the graph, you see in box plot format the results of an M5 filter as coming from our follow-up measurements in the in-laboratory experiments. The green marker gives the efficiency of the filter as measured in this system. So what we see, we have the same efficiency profile, although the efficiency is a little bit higher. And this can be explained by the fact that the filter we've tested here in the air handling unit is at new state, and we also have a large difference in airflow. In the air handling unit, we are about 4,000 cubic meter per hour, while in the test setup for residential filters, we were at 150 cubic meters. When we wanted to measure the efficiency of the F7 folded panel filter, we noticed that the filter was severely damaged. So apparently it couldn't handle the airflow and the filter medium was ripped out of its frame. So we replaced it with a new filter, but with a reinforced version. And then we did our measurements again. Here we see again the measurements on top of our previous results from the follow-up measurements. In blue, you see the efficiency of the F7 filter. And here you see again the same profile and a bit higher efficiency for the same reasons as I explained to you before, difference in airflow and the new state of the filter. If we're looking at the combined efficiency of the M5 and the F7 filter, we see only a marginal increase in efficiency. But this is logic since this coarse filter is mainly affecting larger particles and is mainly there to protect the system and this fine filter. In a second setup, we replaced these M5 and F7 filters by one F7 filter EPM 2.5 70% back in front of the ventilation system. And here you see also the results. We did the measurement twice, once at new state and once after 2 months in use. The blue marker is the new measurement at new state. The green marker is after 2 months in use. Again, we see the same profile, but a higher efficiency. And we also see that after 2 months, the efficiency slightly decreases. And that's also something we saw from our measurements in our in-laboratory setup. Typically, an efficiency of such a filter is initially high, will decrease during the first months in use, and will then again increase. We were also able to measure the pressure drop in the first setup and the second setup by the building management system. And so in this table, we see the results of this pressure drop measurement. And there we see for the combination of a coarse filter and a fine filter that it ends up at 110 Pascal. If we look at the F7 EPM 2.5 70% back filter, we see that we have in use state 96 Pascal and approximately 100 Pascal after 2 months in use. So in general, the pressure drop over this single stage back filter is lower than over the combination of a coarse and an F7 fine filter. And we also know from our in-laboratory experiments that over time, this pressure drop over a back filter will increase less than is the case for the combination of a coarse and an F7 folded panel filter. So this means that an F7 back filter is also an interesting alternative for air handling units. And finally, we also looked at an F7 back filter at different airflow rates. We measured it at 3 different airflow rates, and we can say that there is actually no significant difference in efficiency over these 3 flow rates. So we have a filter that's quite consistent in its performance. To end these presentations, I will give you our conclusions and recommendations. So first of all, we see a good consistency between the results of the both projects. So this means that the recommendations from our Out2In project focused on residential systems can be transposed to air handling units. Regarding filters, as you notice, for residential system to deal with PM2.5, we need to install an additional filter box. In air handling units, this is not needed since these options, either a combination of a coarse filter and a folded panel fine filter or a back filter, can be directly installed into the ventilation system. For this installation, it's very important to consider structural stability of the filter, especially for folded panel filter, as we saw that the filter can be damaged if it's not sufficiently robust to handle the airflow. Also, the airtightness of the connection of the filter and its housing is very important, since air that is passing the filter will not be filtered and will decrease the general efficiency of the filter inclusion in an air handling unit. And especially for air handling units where more filters are placed along in a larger frame, it's very important to also consider this air tightness between the filters in this frame. And especially for back filters, it's important to install them in a vertical position. If you put them into a horizontal position, you have the risk at lower flow rates that the backs will close themselves and inflict a higher pressure drop. And during installation of back filters, it's very important to pay attention to the fact that most of the time they are installed in a U-shaped profile. So you need to squeeze these backs together before inserting the filter in the U-shaped profiles. Otherwise, they will cut into the filter medium and already damage the filter before you can start using it. Regarding replacement, the advantage is for air handling units that in most of them, the pressure drop over the filters is monitored by a building management system, meaning that you can go to targeted filter replacement. This is something that is not the case for residential systems. So there you are mainly dealing with time-based replacement of a filter. And last but not least, we did not test electrostatic precipitation in air handling units, but given the efficiency we measured for it in our in-laboratory setup and also the lower pressure drop, it's a very interesting alternative. And the space to incorporate such a system is most of the time available in air handling units. So it's worthwhile considering. If you want to know some more information about our project about residential filters, you can find it in a publication that is available in the AIVC database. Hereby, I would like to thank you for your attention.